We are going to analyze here the stability of the two previous methods, numerical methods we have seen before. One is the forward Euler method, that is an explicit method, and the other one is the backward Euler method, the implicit method. So that we can see that both approximations, even though the strategy we are following is pretty much the same, they have important differences, and this difference that may make these two methods having quite important differences, especially related with the stability of the method, as we'll see later. And we are going to analyze the stability of this method. Yes, use a precise example. We are going to use an example for that. And the example I've chosen in this case is a very simple differential equation. This is the one we do have here. And as this is so simple in this case, we are going to first analyze it analytically, so that when comparing with the numerical method, we can see more easily if the numerical method goes in the right direction or if it goes in the wrong direction. And here actually we can use the variable separation method to analyze that equation, and this is what we're going to do now. So in order to do that, we are going to bring to one side everything which depends on y. So everything which depends on y, so we're bringing this y to the other direction, that was dividing, and then everything which depends on t, in this case differential t, is going to the other direction, so we have minus differential t. Now we are going to integrate that equation. We are going to make the integration, and we're going to plug here, considering the limits in the integrations, the initial condition we do have in this differential equation. And that basically is the following. When time is 0, we have the y is 1, and we're going to calculate at any time what's the value of the y function. So once we have that, now we're ready to do the integration. They are actually very easy integrals. So here we have log n of y, and the limits are 1 or y, and the other hand we have minus t, and the limits are 0 and t. So again we have log y minus log 1 minus t. So this is what we have. In this case, the log of 1 is 0, so we have log y is minus t. Or if we clear from here the y, what do we have is the following. Y is the exponential of minus t, and this is basically the result that we're getting. So as you can see here, this is the exponential, and actually it's pretty much easy to have the graph of these results. So basically what we have that initially we have that at t equals 0, we know that the function, the value of the function is 1. So here in the y-axis I am just drawing basically the y function, and then it decays exponentially with time, and at time t going to infinity we have that the function decays to 0. So that's the result that we have, and that's important in order to compare with the numerical method. So now we are going to apply the two methods we have derived before. Let's start with the forward method, and that's what we are going to do next actually. So this is actually the forward method. This is an explicit method that we said before, and this is basically the method that we derived before. And basically what we have to do here is we are going to apply that method here, and basically means that the y function at the step I plus 1 is equal to the y function at the step y. This is what we have here, plus delta t, the time step, times f. Remember that f is this function here. In your definition of the differential equation, we do have that the derivative of y with respect to t is the f function. In this case, the f function is minus y. That's why we do have minus y here times delta t. Okay, this is the result. So we can writing this way as it's said here. So this is the method that we're going to apply here, and basically you can see that when delta t, for example, it's quite big, let's say for example it's bigger than 2 in this case, for example, you can see that this becomes bigger than 1, in this case negative, and bigger than 1. The absolute value of this factor here becomes bigger than 1. What does it mean? It means that the absolute value of this y at step I plus 1 is bigger than the absolute value of y evaluated at time y. But this is not what we do have. In the result, we did have that the exact result goes that the case exponentially with t basically means that the wave function at the next step should be smaller than the wave function at the previous step. But this is not what we have for such cases when actually when we consider that particular ranges of time steps, and for that particular time ranges we can see therefore that the wave function at the next step becomes bigger, or the absolute value of the wave function becomes bigger and bigger and bigger, so that what we have that the absolute value of y will go to infinite. It does not decay to 0, and that's what we call to be the method to be unstable. So basically, it means, or the kind of result we are getting here, it's more or less is something like that. Okay, here I'm trying to plot what kind of result we would expect here when applying that method. Again, consider that the initial point is this one. Let's suppose that this is the one value is located here, and the exact result would be something like that, exponential decaying function. And what we have here is something like that. When going from one point to the other, let's draw it with a yellow, with an orange color. When one point to the other, we are getting a bigger value, and actually it changes the sign because this factor here, which is multiplying the wave function at time or I, it's negative. So will be when starting from the initial point here, the next time the value of y at the next time step will be something like that. The y value at the next step will be something like that. So as you can see, it will be higher, 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 and higher, and that would be that's the kind of result that we have for such time steps, so that you can see here it's clearly unstable. And instability of the method is something that you cannot see when you draw the method itself. Something that you have to analyze, and it actually will depend on the kind of time step you are considering. It's some pathological problem inside the method itself. Of course, when you are considering time steps smaller than these ones, you don't have such a problem, such instability problem. The instability problem in this case only arises for such a particular time step ranges. So this is the behavior of the forward Euler method with respect to stability, and let's see what happens with the other method, which is the backward Euler method. So basically here we are doing pretty much the same. We are applying directly the method. This is an implicit method. Again, we are applying here. Again, this f function, in this case, it's minus y, but in this case, evaluated at time I plus 1, and the y function should be y evaluated at time I plus 1. That's why we do have this y function evaluated at time I plus 1. And as we have said here, it's an implicit method, which means that we have to work in the method deeper in order to clear from the method the value of the expression for the wave function evaluated at time I plus 1. So in order to do that, basically what you have to do is bring that part to the left. So we bring that part to the left. This is the result we have, and now we are ready now to clear the value of the expression for the y function evaluated at time I plus 1. And we're doing that. This is the expression for the method when this is applied to a particular problem. And in this case, you can see we don't have the pathology which arised in the previous case. Even though delta t becomes higher than 2, for example, in this case you can see that the absolute value of the y function evaluated at time I plus 1 is always smaller than the y function evaluated at time y. That's recovering the exponentially decay of the exact result we just derived at the beginning. So this method, as you can see, it's stable. It has for any time step you are considering. So of course it's a little bit more complicated, you can see, because we need to work a little bit more deeper in order to clear from here the wave function evaluated at time I plus 1, while in the case of the explicit method it was more straightforward, but more stable. In general, actually, all implicit methods, which actually, if you remember, we're incorporating somehow some information from the next step we want to evaluate. In this case, we're incorporating the information of the derivative of the next step we want to evaluate. And that actually makes that method to be more stable, so behaves much better. Implicit methods behave much better than the explicit method with respect to stability.